All right, we're going to continue with some of our operations on logarithms. And now we're going to take a look at properties. So just with exponentials and the laws of exponents, we also have laws or properties of logarithms. So let's first start again with the definition of a logarithm. Okay, so if I give you the writing of y equals log base a of x. Okay, remember, by the fact that I can turn any logarithm into an exponential by wrapping this around, this means the same as a, the base a, raised to the y power equals x. Some people prefer to write these in the, okay, by the reflexive property, they mean the same thing. And so you could say that the base on the logarithm raised to the answer is x. So that's one of the facts. So if I can write a logarithm as an exponential, the properties of logs are very similar to the properties of exponentials. Now let's also kind of think about this for a second. So some of these properties, okay? So let's do this. Properties of logarithms. So let's write them all down, and then we're going to practice using them. First property, log base a of 1. Well, if we think about the fact that any logarithm I could rewrite as a to this answer equals x, this would be like saying a raised to what power equals 1. Well, a raised to the 0 power equals 1. So there's our first log property. So keeping that in mind, what would log base a of 1 be the same as? I just wrote that down. Didn't mean to write that one down. Meant to write this one down. Log base a of a. Well, if I follow the same property, a raised to what power gives us a? A raised to the first power gives us a. Okay? All right. So now let's take a look at the next property. Let's say I give you a raised to the log base a of some number. I'm going to call it m. Well, if the base on the exponent is the same as the base on the logarithm, when I unwrap this exponent and make it the same, when this base on the exponent is the same as the base on the logarithm, our answer is simply m. Okay. So think of it this way. If I give you then log base a of a to the r, I'm going the other direction now, this would have to be a raised to what power gives you a to the r? It would have to be r. Okay. Now let's take a look at, I'm going to keep going, I'm going to write some other ones. I'm going to take a look at, with exponents, whenever we're multiplying and the bases are the same, we add exponents. So with a logarithm, if I give you log base a of a product, well, in exponents, whenever we multiply, we added the exponents. In logarithms, whenever we multiply, that's the same as adding the individual factors. Similarly, let's think about division. If I give you m divided by n, well, with exponents, whenever the bases were the same and we divided, we subtracted exponents. So with logarithms, whenever the bases are the same and we're dividing, we subtract logarithms. So this is called expanding, because we've taken one term of division and we've expanded it out to two terms. Okay? I'll put this one in here. Well, let's say we have a power. Log base A of m raised to a power. Well, with exponents, whenever we had an exponent raised to a power, it meant multiply. So in this case, this r is going to come all the way out to the front, and we're going to multiply the power times the logarithm. And we're going to be practicing these. So I just want to make a table, a giant pool of all of our various tools here. And then when solving, I'm going to go ahead and give you this theorem now, and then when we solve, this will help. We also have this log theorem, logarithmic theorem, and it sort of seems to make a little bit of sense. Let's say I have two parts to it. The first part says if two things are equal. Well, we know if they're equal, they're the same. And we know from algebra, if they're the same, you have to treat them the same. So whatever you do to one side, you have to do to the other side. So if I choose to take the log of any base on the left side, it could be log base e, log base 2, log base 10. If I take the log base a on the left, I have to do the exact same operation on the right. So that's one of the theorems. If two things are equal, whatever I do to one side, I do to the other. So I'm going to take a log of both sides. Conversely, I could go the other direction. If log base a of m is the same as log base a of n, well, we know if two things are equal, they're the same, so everything about them has to be the same. So if I have a log with the same base on the left and the right, that must imply whatever I'm taking the logarithms of are the same. Okay. And then the last piece of information before we start practicing is what is called the change of base. And what it allows you to do is it allows you to take any base, and I'm going to show you how to do this. I'll do some examples. And it allows us to change it to another base so that we can use a calculator. I don't know if you can see on this calculator. On this calculator, you should have a couple of buttons. You should have a logarithm button, and you should have a natural log button. Okay? This is in TI-89. So this one, let me grab. Hang on, meant to grab, there's an 83. Okay, so on your calculator, on this TI-83, you'll notice on the left-hand side, down this left-hand side, you'll see a button that says log, and then you see a button that says ln. So on the button that says logarithm, you'll notice right above it, it says 10 to the x. That's because log means log base 10. On the button that says ln, right above it, it says e to the x. And that's because that means the base is base e. So this is going to allow us to use these buttons on your calculator. And we can do it in class. But the change of base formula will allow us to use a calculator. Now your phone, when you go into your phone, and I go into my calculator on my phone, you'll also be able to, if you have your phone, you should be able, and it's got all the operations, add, subtract, multiply, divide. If you turn your phone sideways, hello, come on. How come it's not? It doesn't want to cooperate at the moment. There we go. Okay, if you turn your phone sideways, and I'll hit an all clear, you may also notice that you have a lot of things on here that you haven't seen yet. But you should also find a log button and a log base E button. So I have an e to the x and I have a 10 to the x. So if I hit the second key and I hit, then you'll notice it says log base x, log base y. So you'll be able to use your calculator on your phone if you need to as well. Okay. All right, so the change of base formula looks like the following. Change of base formula says, if I give you log base A of any number, I'm just calling the number m because that's what your author chose. Now, I think of this as a fraction. Think of this line that's right here underneath this logarithm. Under the word log is sort of this natural line where m is above the line and a is below the line. So if I think of that line right here as a fraction bar, then I can either use the log base 10 button on your calculator and divide it by the log base 10 of whatever your base number was. Or if you prefer, on your calculator, you could use the natural log button and the natural log of A. Okay. So I'm actually going to start with that. I'm going to start with using that. So for example, let's use the change of base. Am I off the screen? Yes, kind of. I'll bring this down a little bit. So we just want to use a calculator. So you can either use for function calculator on your phone, but then turn your phone sideways. And let's say I ask you to find log base 5 of 18. Well, this is not going to give us an exact answer. This is number 72. What do we know before we estimate? We know 5 to the 0 power, anything to the 0 is 1. We know 5 to the first power is the number 5. We know 5 to the second power is 25. So what we can deduce is the number we're looking for has to be 18. So we want to know 5 to what power gives us 18. That's what we're trying to figure out. So what we can do is we can use the change of base formula. So I'm going to choose to use either one of these buttons, does not matter. And so I'm going to write this as log base 5 of 18 is exactly the same as, if I choose to use my log button, log base 10, I would say log base 10. Remember, if there's no base written, it's assumed our base number system of 10. And divide that by log base 10 of 5. And now you can let the calculator do the work. I go log, so on your calculator it looks like this, log, and it'll put a parenthesis there. So you put the number 18 in, make sure you close the parenthesis, hit divided by, log, it's going to throw the parenthesis up there. Make sure you put the 5 and close the parenthesis. Log 5. And I ended up with 1.7959. So this is really close to 1.8 if I round to the nearest tenth. And so I would suspect that if I take 5 and raise it to the 1.8 power, I'm going to get a number really close to 18. 5 raised to the 1.8. Okay, I don't know if you can see that. Equals 18.11. So we got pretty darn close. I rounded up. Therefore, it didn't surprise me that I ended up with a number a little bit larger than 18. So that's how the change of base formula works. And you could have used the natural log button on your calculator, and I guarantee you would have gotten the exact same answer. Okay. Okay. So let's take a look at and practice using some of the properties. All right, so we're going to just sort of practice at the beginning. I know I started at the end, but I want you to see how to use your calculator. Let's practice some of these properties. So use the properties to find the exact value. Do not use a calculator. Use the properties of logarithms. So this is in section 1, problems 1 through 28. So let's say I pick number 2. Just start at the beginning. Log base 2 of 2 to the negative 13. So what I'm going to do is I'm going to sort of go, okay, which property says log base 2 of 2? So where is the base the same? Log base A of A. Log base A of A. Here it is. Log base 2 of 2 raised to the negative 13 power should equal negative 13. And you're done. And this is actually numbers 13 to 28. So this is number 12. If I take a look at number 18, e raised to the natural log of 8. Well, one aspect I highly recommend you do for a while is as soon as you see natural log, turn it into log base e. So this is the same as e raised to the log base e of 8. Okay, so I'm looking for an exponent. A raised, well here it is right here. E raised to the log base e of some number. Should just give us that number. So a lot of what you're going to be doing right away is just practicing using some of these properties. So let's say I give you problem number 20. Number 20 says simplify. Log base 6 of 9 plus log base 6 of 4. So I'm adding two logarithms together. These are called like terms because we can always combine like terms and they both have the same base, so they're considered alike. So if the bases are the same and I am adding, the bases are the same, here it is, and we are adding, that's exactly the same as combining them to like terms, but addition turns into multiplication. So the base stays the same. And anytime I'm adding like logarithms, it's the same as combining them into one logarithm and multiplying together. In this case, 9 times 4. So that's the same as log base 6. 9 times 4 is 36. And now we can write that as an exponential. Remembering, of course, log base a of a number, right? We can rewrite it as 6 raised to what power gives us 36. So in this case, 6 squared gives us 36. Okay, so we're using the properties to simplify. So same idea with number okay. Alrighty, so that's how we start off using some of those. Then in the next section, they gave us a couple of facts to play around with and to use. So in our next section, and whether I give you a book, whether I give you a handout, the properties are never going to change. Let's say I tell you that the natural log of 2 is represented by the letter A, and the natural log of 3 is represented by the letter B. And I would like you to find the natural log. Find the natural log of 2/3. 2/3, yes. Well, I've got a single logarithm that's being divided. So I have a single logarithm, here's multiplication, here's division, of division. Therefore, I can separate this out, and division implies subtraction. So this would be the natural log of the numerator minus the natural log of the denominator. And so now, according to the information that we've been given, natural log of 2 is A, natural log of 3 is B. And you're finished. Finished. Let's try this one. Oh, I jumped ahead. That's okay. Natural log of 27. So we want to think about how can I create the numbers 27 only using 2's and or 3's. Well, 2 does not go into 27 evenly. 2 raised to a power is not 27. 3 goes into 27 evenly. Or 3 can be raised to a power, get 27. So I'm going to rewrite this as natural log of 3 times 3 times 3, or you could have said 3 cubed. And now we have an exponent raised to a power. Anytime I have a logarithm or I have a power, that power catapults out front, and it becomes r times the logarithm. So in this case, this exponent catapults out front, and we are left with 3 natural log of 3. And we are told early on that the natural log of 3 is being represented by b, so this is 3b. Or if you prefer, some of you may have said, well, 27 is 3 times 9, and that's 3 times 3. And now, if I have multiplication, we know anytime you have a logarithm with multiplication, that implies addition. So I could have written this as natural log of 3 plus natural log of 3 plus natural log of 3. And now that would be the same as b plus b plus b that's the same as 3b. So either way, you would have gotten the same result. Does not matter to me which way you use because they're both valid. Okay, so they're both statistically sound. All right, so if you have a question when you're going through this section, I want to do 36. Because I do want to refresh your memory on powers. This says the natural log of the fourth root of 2/3. And I mentioned it in, maybe I didn't mention it in the last video, not remembering which one I've done with you guys, but just to refresh your memory, a root is the same as a fractional exponent. So this is exactly the same as 2/3 raised, whatever this index number is, becomes the denominator. So if it's a fourth root, we raise it to the 1/4 power. If it's a square root, we raise it to the 1/2 power. Fifth root, we raise it to the 1/5 power. And now this follows the same law that we did a minute ago that says anytime you have a logarithm raised to a power, bring that power out front. So now this 1/4 is going to come and catapult out front times the natural log of 2/3. But we're not finished because we talked a minute ago about anytime you have a natural log of division, division implies subtraction. So this would be the natural log of 2 minus the natural log of 3. And since the 2/3 was in parentheses, we need to make sure that entire subtraction of logarithms is in parentheses. Or distribute the 1/4 to each term. Okay, so sometimes you can expand logarithms. Other times we can condense logarithms. So I'm going to keep going with the same idea and we'll just keep practicing. Now instead of A and B, we're going to actually use some numbers. So let's take a look at 38. Okay, the next section talks about write as the sum or difference of logarithms. Okay, so let's say I ask you to write using sums and or differences of logarithms. Okay, so here's number 38. It says log base 3 of x divided by 9. So we just did a problem of division. Let's just follow that along. If I expand this, this should be exactly the same as log base 3 of x. Division implies subtraction. Log base 3 of 9. And we cannot do anything with the log base 3 of x. We cannot do anything with that because the base, and we have a base that's a number, and we're taking that to a variable. Well, look at the other one. Log base 3 of 9, we can simplify. Because that's the same as saying log base 3 of 9 equals what number? So if I exponentiate, if I turn it to an exponent, if I exponentiate this, this is the same as 3 to what power equals 9. So 3 raised to what power gives you 9? This is the same as the number 2. So now we are left with our final answer of log base 3 of x minus 2. So anytime you have the base on a logarithm, the same as the base of the exponent, you need to simplify this. Okay? So if I keep going along here, I'm going to take 44. Forty-four says the natural log, so we automatically know what the base is. The natural log is going to be base e of x e to the x. Okay, so we've got to ask ourselves, I have one logarithm, it just happens to be log base e, but I have multiplication going on in here. So multiplication implies we should pull it apart into addition. So this would be the same as the natural log of x, wherever there's a multiplication, I'm going to put an addition, the natural log of e to the x. Now, if you prefer, you could rewrite natural log as log base e. Natural log is log base e. And the reason I did that is, when the base on the logarithm is the same as the base on the exponent, our answer will always be whatever that power is. So here, the base on the logarithm is e, the base on the exponent is e, so this answer is just x. Nothing can happen on this log base e, so I'm just going to rewrite it as the natural log of x. Okay, so we're just manipulating and using the properties. Okay, and then they could get a little more complex. I'll take a look at number 52. 52. It just says log, so that would imply log base 10. And then it's a fraction. Okay, so when we think about fractions, we'll have to think about what that means in terms of a logarithm. This numerator is x cubed times the square root of x plus 1. The denominator is x minus 2 quantity squared. So I'm going to use the log properties since we're dividing. If I have a logarithm of a fraction, here it is, that's this fifth property. A fraction means we want to separate it out into two separate logarithms separated by subtraction. So I'm going to rewrite this. Logarithm, the numerator, whoops, that's an x cubed. And according to this property, then it would be minus whatever our denominator was. Log base 10, x minus 2 squared. But we're not finished, because when we analyze each of these terms, this first term has multiplication in it. So anytime we have multiplication, I have to take that and split it apart into two addition problems. So this becomes log x cubed plus log square root of x plus 1. And I'm just going to bring the other one along for the moment. Well, we're not finished yet, because in the first term, terms are separated by plus or minus, this is an exponent raised to a power. So I need to bring that power down. Then I've got to think about how else could I rewrite a square root. Well, a square root has an index number. This is a square root. It has a little 2 right there, which means I could rewrite this as a power. X plus 1, since it's square root, it would be the 1/2 power. And now I'm going to employ the same property we did a minute ago. If I have a logarithm to any base of an exponent raised to a power, that power comes out front. This power comes out front. So we are now left with a 3 out front, a 1/2 out front, and a 2 out front. 1/2 log x plus 1 minus 2 log x minus 2. And I cannot simplify any farther other than if I chose to find a common denominator, but then I'm kind of going right back into what I did before. So if we're rewriting as a sum or difference, here's a sum, here's a difference, you're good, you're fine, you're finished. Okay? So with expanding, it's the idea of we're taking all these combinations of multiplication, division, or power, and we're expanding them out. Now let's go the other way. Let's condense. On this next example or two, we're going to condense and write it as a single logarithm. We're still going to use our log properties. Write as a single logarithm. So we're going to use our properties. So here's number 52. 2 times log base 3 of u minus log base 3 of v. And we learned in algebra to combine like terms. Terms are separated by a plus or minus. These are considered like because their bases are the same. So if the bases are the same, I can use the properties. Okay? Well, since I have a 2 out front, I kind of have to look at it backwards. Since I have a 2 out front, I'm going to first take this 2 and catapult it back and make it a power. Okay, so I now turned into the multiplication. Now subtraction implies when I want to put them together, it changes to division. So I'm now going to combine like terms. So these both are log base 3. And the first term is your numerator, and your second term is your denominator. And now I have written it as a single logarithm. Okay? And of course they can get a little more complicated. So let's take a look at, here's number 66. If I turn the page, I have 21 log base 3 of the cubed root of x. Plus log base 3 of 9x squared. Minus log base 3 of 9. Oh, interesting, because that's just a number. Okay, now I'm supposed to put them all together as a single logarithm. So what I notice is I can rewrite this first as, I'm going to leave this alone, 21 log base 3. And I'm going to write this as an x to the 1/3 power. I know it's the denominator is a 3 because the index number is a 3. I'm going to do this one slowly. Now I'm going to bring and I'm going to catapult back my 21. So this will now be log base 3x to the 1/3 third power, but I brought the 21 up. So now if I simplify, 1/3 of 21 is 7. Now this is good, because now addition implies multiplication. So instead of adding log 3 of 9x, I'm now going to multiply by 9, x squared. Instead of subtracting, I know subtracting implies division. Divide by 9. And now I'm going to simplify. I'm going to combine things together by laws or properties of exponents. X to the 7th times x squared would be log base 3 of x to the 9th. And then notice these 9s actually reduce. So we are finished. So we wrote it as a single logarithm using the properties. Okay, then the last part of the homework is using change of base. Okay, so next section we will be going through and using a lot more of the solving equations, but this section is all about using the properties. So I would suggest you have a list of the properties next to you as you're doing the homework or the lab. All right, and next section we're going to take a look at solving equations. See you then.